So to start off, when I say secant line, just to remind you of the definition, what a secant line is any line that cuts through an object at more than one location. Usually we'd say it cuts through a curve. It intersects a curve at more than one location, like that there. That would be a secant line. And so some of the other words you might hear me say today are a tangent line. A tangent is any line that intersects an object at only one location. So that would be forming a tangent line. Whoops. So those are the terms you're going to hear me say a lot today. What I will not be saying a lot of is diameter, radius, or chord, but those are words that are normal when dealing with circles in particular. A chord would be very similar to a secant line, except that it has endpoints on the circle, whereas a secant line would pass through it. So secant line, again, a secant line is a line that passes through 2 points on a curve. Now, with that secant line, we're going to be measuring today the slope. The slope of the secant line is what we're going to call the average rate of change. And that's in particular what our goal is to talk about the average rate of change or the secant line today. Average rate of change. Let's get that in there. There you go. So that's what we're looking at today in particular. So to begin, the formula, if we're looking at the average rate of change as in the slope of the secant line, if that's what we're going to be looking at, then let's talk about our slope formula from Algebra 1. If you remember, we had the equation y equals mx plus b for the equation of a line. Y equals mx plus b. That was our equation of a line. The m was the change of y's over the change of x, also known as rise divided by run. And so we'll have the change of y's over the change of x's. That's going to be our formula to find the slope of the secant line or the average rate of change. Now, once we find that for our secant line tonight, we're going to be using this point slope form. So typically students in Algebra 1 spend most of their time dealing with the slope intercept form, which is y equals mx plus b. But tonight we're going to be using point slope here, which also is in Algebra 1, but students aren't as familiar with it. I'm going to be using that as I show you equations today, just because it's a whole lot easier to find a point exactly on the curve, because we get to pick our point here and here. There's our x and y value. That would be representative of the point x1 comma y1, and the slope is obviously the m. So we'll be plugging those in today as we go. Okay, with that, let's actually get working. That's what you came on for. So let's get started. Example 1. It says determine the average rate of change, or AROC, you might hear me say tonight, between the points -1, 1.5 and 0.3, and then do so again with the points 0.3 and 1.6. So if you wanted to, we could look at this as a table, and I've given you some the x values I've given you. It's -1, 0, and 1. The y values I've given are 1.5, 3, and 6. Those are the coordinate pairs given in this problem. What we want to do is find the AROC. So one of the ways you'll see me do this in class, and I'll do it here, is I'm going to do a change of y column here, and on this side, I'm going to do a change of x. So from -1 to 0, how much are we increasing by going from -1 to 0? And if you can just come off mute, just throw it out there. How much we change it by?
×2.
Sorry. Oops. For those who are just joining, whenever I ask a question, if you just want to come off mute, throw it out there, that'd be great. Or you can send in the chat. I'm not sure if the chat will pop up, so if you come off mute, that would be best for this. How much are we changing from going from -1 to 0? Well, I'm not hearing anything. I'm going to just assume you realize that's a +1, and here we also have a +1. So if both these values, the x's are increasing by 1, and when I look at the change of y's from 1.5 to 3, that's a change of 1.5, and from 3 to 6, that's a change of 3. So the first A rock, and I'm going to go over here now. Maybe I should change colors just to see clear. What I'm now going to do is find an A rock. And so A rock was the change of y's divided by the change of x. And so we're going to have two different values here. The first one would be 1.5 divided by 1. And the second value would be 3 divided by 1. And so the first thing we're going to do after finding these values, so it says here, determine the average rate of change on the first interval is 1.5, and the second interval would be 3. Okay, so this is the A rock on interval 0 or -1 to 0, and this would be the A rock here on the interval from 0 to 1. And by the way, we could do an A rock if you wanted to on an interval. We could do one more here. I'm gonna just go ahead and do it on the interval from -1 to 1. You could do this as well, where you do the change of y's, which would be 6 minus the 1.5. And then the x's, 1 minus a -1. We could do that as well. So 6 minus 1.5 would be 4.5. That would be divided by 2. So that would here be 4.5 divided by 2, which we could reduce to become 2.25. So you can find that A rock at all those different values. So what do I want to determine from that? What's important for you to be able to determine from those values is this: that the slope, since the slopes were positive, we're going to have an increasing function. So right here, I've now thrown in the graph. You didn't have the graph before, but as you can see, these points here, these are the same points from part A. These are the points from part A. From part A. Since the A rock was positive, this is an increasing function. So this secant line right there, let me try that again. That was ugly. Let me try that again. This first secant line from these 2 points through there would have that slope of 1.5. Okay, the second slope we found of 3 would be the slope of this secant line right here of 3. The third A rock I found would be the slope between the second 2 points. So now what I'm going to do is plug these into equations. This would come through, this is going through the point. Here, I'm going to plug in the point 1, 6. The way you would do that is in parentheses, you'd say y minus y1, which I'm going to say is 6, equals 3, parentheses, x minus x1, which happens to be a 1 there. If I use the point x1, comma y1 as 1, comma 6. That would be the equation of that secant line there. That would be one equation of a secant line right there. That's a secant line. And the other, if we wanted to find that in blue, if you had to know the equation of this secant line, we could plug in a different point. I'll plug in the 0, 3. Let's plug in the 0, 3 here. Then my equation would be y, not y equals, sorry. Use my formula here. Okay. Y minus, I'm plugging in the 3 here for y, equals m, which is 1.5. And then it would be x minus 0, which could be simplified to simply 1.5x. So these would be my two secant lines. There's one there, and my other secant line up above. That would also be the secant line. Okay, so I don't know, it's been a long time since we worked on these. These were literally the very opening assignments out of the gate. We were looking at secant lines, and so that's what it's all about. So what can we conclude? Because the slopes were positive, we can conclude that this is an increasing function. This function's name is f. So we could say f is increasing on the interval -1 to 1. That's what we could determine because the A rock was positive. Let me actually go ahead and do this so we can see why. Since A rock was positive. So if you have an increasing A rock, the function has to be increasing. If you have a positive A rock, let me say that again. If you have a positive A rock, the function has to be increasing, because that's what it means. The slope of the curve, if you were to take a straight edge slope on the curve, you would get something that's moving up. And for that reason, the function is increasing. So now part C, there was a second thing we determined. So here are my secant lines. I've added them on now for us. It says, considering the A rock on the second interval increased from the A rock on the first interval. What this means is, remember the first M we found, I'll just call it M1, was 1.5. And the second A rock we found was 3. Way back on part A, right here. Here was my first. Here was my second. I'll call this M1. And this was M2 there. Since M2 was greater than M1, or the second interval was greater than the first interval, we could say that this function is concave up. F is concave up. Since M2, which was a later interval, was greater than M1. So we called this, if you remember, we called this delta A rock. I don't know why I put that in parentheses. Hang on 1 second. Here we go. Let me take it away. We called this delta A rock in class. If delta A rock is greater than 0, that means the change of the A rock. So if you move, as your interval moves to the right, as your domain increases, if that delta A rock is greater than 0, then the function is concave up. Just the same, if your delta A rock was negative, you'd be concave down. So this function is concave up because the second slope was greater than the first slope. The later interval increased at a greater rate than the first interval. Okay, so I believe that's it for my example 1. And I'm going to just show you something on. Okay, let's fill this in here. It says, therefore, if the average rate of change of a function is positive, meaning the A rock greater than 0, the function is, and you fill in the word. What word do you think should belong in that first blank?
Concave up.
So it will not actually be concave up. This one would be a different one. If your A rock, which is similar to slope, if your slope is positive, if you have just a slope that's going up, what could you tell me about the function?
Increasing.
There you go. So it could be any type of a curve. But if that's the function there, f, let's call it, if it's going up, then it is increasing. So we'll say this is increasing. Conversely, if the average rate of change is negative, meaning A rock less than 0, then the function is decreasing. Secondly, if the change in the average rate of change, so notice this here, this isn't a typo, if the change in the average rate of change. So now we're talking about delta A rock. If delta A rock is positive, then the function is concave. Well, let's see here. Let's just draw this out. If we have some function, I'll draw one that's concave up. If we have some function here, I'll call it g, and it's concave up. What you could notice if you did a bunch of secant line or tangent lines, here is what I'm kind of drawing. If I did a bunch of tangent lines, you'd notice that each one has a slope that's increasing from the previous. Each one's increasing. If the change in your average rate of change, so if this is like M1, this is M2, this is M3, this is M4, if those are increasing as you go around, then the function is concave up. Therefore, if the change in the average rate of change is negative, meaning A rock is less than 0, the function is then concave down. Those are very important concepts that you have down by heart, that you just know, because that's what a lot of your observations are going to be concerning with the A rock. We're not just going to find A rock for no purpose. When we find A rock, the purpose will be to determine if it's concave up or concave down, which it will ultimately blend into calculus. So before I work another one, I created a Desmos just to show us this. So here's our first example. What I'm going to do is I'm going to move my secant line to the right. And you can see as I move to the right, my slope continues to increase more and more. The slope of the blue line increases. And I could zoom out more here so you can see more points on the curve. As I move this curve, the secant line along, you can see how the slope is increasing. Because it's increasing, this function would have to be not only increasing, but concave up. So because my slope here, the blue line is positive, it's an increasing function. Because as I move to the right, the slope increases from the previous slope, it would be concave up. So that's example 1. Now let's go take a look at example 2. It says determine the A rock between the points shown in the table. So to go a little bit quicker through this, let's see here. I'm going to go over here and I'll do change a y. Change a y. So from 0 to 1, we increase by 1. Here we increase by 2. Here we increase by 4. And finally here we increase by 8. If I look at my change of x column, I'm increasing by 2. I'm increasing by 2. Increasing by 2. And finally increasing by 2. So remember now, to find your A rock, you take the change of y divided by the change of x. So here I'm going to do A rock. So this will be 1/2. Here this would be 2 divided by 2, which is 1. Then 4 divided by 2, which is 2. And then 8 divided by 2, which is 4. If I wanted to go further and talk about delta A rock, delta A rock, I see I go from 1/2 to 1. That's an increase of 1/2. Then I go from 1 to 2. That's an increase of 1. And then I go from 2 to 4. That's an increase of 2. Okay, so what can we determine about this function? We're going to call this one f2. What can we determine about function f2? Tell me about the A rock. This A rock, these A rocks are all greater than 0. What does that mean if it's greater than 0? If y'all are typing into the chat, let me see. I'm not sure if it's coming up on my screen. Chat. Let me open that up. All right. I don't know if that's from the previous or this one, but it's not coming up on my screen. So I'm not able to tell if y'all are in the chat. What can we determine if the, I wrote that wrong. I wrote delta A rock there. Sorry. If the A rock is greater than 0, what does that determine about our function f2 here? Any takers willing to come off of mute?
Delta A rock or A rock?
A rock itself, sorry. A rock.
Increasing.
This means it's increasing. Good. Thank you, Sion. This is increasing. Okay, now let me get this right. This is our delta A rock. If delta A rock is always greater than 0, what can we determine about our function?
Concave up.
Concave up, good. There we go. So this one we would have increasing and concave up. And so before I go to example 3, we're going to start going a little bit quicker here. I will show you the picture. I have this one graphed as well. Here's our second equation. I have a bunch of different points plotted on there, and I'll show you as I start moving the secant lines connecting each of those dotted black dots. As you can see, each secant line that I move on is increasing at a faster rate or a greater rate. The slope increases for each subsequent secant line. That's what makes it why we'd call this function concave up. Not only is it increasing, meaning it's the function's going up over time, but it's increasing in its nature. So each part of this, what's happened to my deal there? Each value is increasing at a faster rate than the previous. Each interval is increasing along the way. So these points, I believe, are all 2 units apart. Let me see this again here. Yeah, each of my x values are 2 units apart. So those black dots, each one is horizontally, has the same distance apart from one another. But as you can see, as I move along, the slope continues to increase. Therefore, we could say concave up and increasing, which would be easy with a picture. The problem is you're not always going to be given a picture. So I want to make sure you're aware of how to find that without a picture. All right. So now that you've seen 2 that are basically the same type of graph, let's now try something new. How about example 3? Okay, if you're trying this at home, make sure you're finding your change of y's and the change of x. Now 4/3 is like 1.333, or you can think of 2 being the same thing as, if you had the denominator 3, 2 would be 6/3. So I first increase by 2/3 to go from 4/3 to 6/3. And then from 2 to 4, I increase by 2. Then from 4 to 10, I increase by 6. And then from 10 to 28, I increase by 18. Little bonus here, if you're seeing the change of x increase by a factor of 3, it looks like it's getting multiplied by 3 each time. What type of function would this be?
Logarithm.
You got it, logarithmic. This is logarithmic. That's a little bonus there. And that's since the x's are being multiplied while the y's are being changed by the same amount. Okay, so now we're going to find our A rock, and then we're going to find our delta A rock. Let's see, our A rock, average rate of change. Okay, so what's happening here? On our A rock, I first have -1 divided by 2/3, which is the same thing as -1 times 3/2. So there's our first slope, or A rock, average rate of change would be -3/2. And then we have a -1 divided by 2, is just -1/2. And then I have a -1 divided by 6, so -1/6. And then I have a -1/18. Okay, now let's do delta A rock. Delta A rock. So going from -3/2 to -1/2, I actually add 1. Think of it as a decimal. This is -1.5. That's -1.5. That right there is -0.5. I increase by 1. So I increase by 1 here. And then from 0.5 to 6, oh man, I don't even know exactly what I increased by. If I from -3/2 to -1, -3/6 to -1/6, I increased by 2/6, so I increased by 1/3. And then from -1/6 to -1/18, I increased by 2/18, which would be 1/9. So here's what I could determine on this one. This one's going to be a little harder. Let's put it together though. This A rock, what I'm looking at is if it's positive or negative. All these A rocks are negative. So what does it mean about my function f3 if the AROC is negative? If the function's AROC is negative, what does that mean?
Decreasing.
It's decreasing because it's basically saying a negative AROC means that it has a negative slope. If the curve were a flat line, it would have a negative slope. Now, obviously, this is a curve, so we don't have slope. We'd call it AROC instead. We'd say it's decreasing. And I'll show you a picture of this in a second. However, its delta AROC is not negative. Its delta AROC was positive. Since our delta AROC is positive, what does that mean about each following slope? It means that each slope, though they are negative, it's not as negative as the one before it. The slopes are increasing, though they are still negative. So though the function is decreasing, the function is actually concave up. And that's because delta AROC is greater than 0. So let me show you visually how this problem looks. This was example 3. So here's the logarithmic function. As you can see, as you look at it, the function is in fact decreasing. It's going down over time, but it's concave up, meaning it's kind of opening like your hand, like a parabola in some senses, pointing up. And so as I move, what I'm going to do is show you the secant lines. Here's the first secant line. As I move the secant line from interval to interval, you can notice that each of the secant line that comes next is less and less negative, meaning it's coming closer and closer to being positive. And I think mathematically, these might be demonstrated. If I open up the folder, we can actually see, here's the slope here, M3. Let me just move this up so we can see it. All right. As I go from the left to the right, you can see this M3 over here. Here it is. The slope is negative 4.5, negative 1.5, negative 0.5. That was the 1/6, if you remember. Actually, I can press the fraction button. You can see it, negative 1/6. There was the negative 1/18. I think I might have did some bad. I don't know. Maybe I just have a different value on the table that I don't have on the chart. Anyways, as you can see it, as we go further and further right, the slope is less and less negative. It's becoming closer and closer to 0 as this function continues to be concave up. The function approaches a horizontal asymptote, so it appears to flatten out because this function is going to have a horizontal asymptote at looks like -2, y equals -2. Let me type that in and make sure I'm right here. Y equals -2. No, what are these counted by? Maybe -4. These are counted by 2s. This graph. That's what in the world? Sorry. Y equals negative. Let's try this again. -4. There you go. That's what it looks like this graph is approaching as we go further and further to the right. Let me get my secant line back here. So anyways, yeah, as we go further and further to the right, the slope would approach 0. It is concave up because it's getting larger and larger, but it would get closer and closer to a 0 slope as we moved further and further to the right. So there you have it. That was example 3. Now let me take these off for the next example here. Well, it's not cooperating with me. There it goes. All right. Example 4. 2 more examples, and then I'm going to kind of wrap it up here. Let's talk about example 4 here. Looking at this function. Let's do the same things we've been doing. So first, let's find our AROC. So I'm going to find the change of y's on the right and the change of x on the left. Now this one, the change of x's I'm seeing are increasing by 1 each time. So that's nice and easy for us. on the right side, from increasing from -2 to 1, I increase by 3. Then I increase by 0.75. And then I increase by, oh no, testing the math here, 0.1875. Which that column would be the same as the delta AROC because we're dividing, excuse me, not the delta AROC. This would be the AROC column because we're dividing by 1. So we'd have 3, 0.75, and positive 0.1875. Okay, AROC column. What you look at or what you observe is whether it's positive or negative. AROC is positive. What does it mean about function f4 if AROC is greater than 0? Someone other than Sion would be great.
Is it increasing?
It's increasing. Good, Jesse. F4 is increasing because the slope of its function, if you will, the AROC, which is kind of very similar to slope, just not a, the only difference is F4 is not going to be a perfect line, so we wouldn't call it slope. It is increasing. That is correct. Now, if I look at delta AROC, I'm changing from 3 to positive 0.75. That means it's a decrease of 2.25. And then I decrease again from negative or from positive 0.75 to 0.1875, which is a decrease. Oh no, here we go. I need a calculator here. I don't know if this app has one. That's most does though. 0.75 minus 0.1875, 0.5625. So this time when we look, our delta AROC values are negative. So what's it mean if the change in the AROC, the delta AROC, the change and the average rate of change is less than 0? What can we conclude about the function?
Concave down.
Very good. Sorry, very good. Concave down. And those are the observations you're going to need to be able to make on the AP exam. Is given a table of data to determine if the function's increasing, decreasing, concave up, or concave down without a graph. So just given the information I gave you, that's what you're going to be able to hopefully determine. So I'll show you this function. I didn't ask, does anybody know, bonus points here, does anybody know what type of function this is?
Exponential.
Let's see. We got a guess that's going to be exponential. Let's check it out. What are we doing? Example 4? Yes, it is. We got an exponential function here. And I left my A over there. Let's go. Okay, so this exponential function, it is exponential. You can tell because it has a horizontal asymptote. It looks like it's approaching. Sorry, my computer's sliding. It's slowing up on me. Why is it not sliding over? Come on now. There we go. You can see it's approaching the line y equals 2. And as I show you, to demonstrate here, the secant lines, which the secant lines are the lines that showing all the AROCs. Oh, slide, there we go. As you see each secant line, though it had a positive slope, each one has a positive slope. That means the function is increasing. That slope of each secant line is getting closer and closer to 0. It's decreasing. That's what the delta AROC was negative. And so that means that this function is increasing at a slower rate, meaning it's concave down. Because it's concave down, it's increasing at a slower rate. And again, I could open these up and show you the slope on this as we go. Just move it up to the front so you can see it as I go further and further to the right. Let me start here at a equals 1. As I slide to the right, you'll see each slope gets smaller and smaller and smaller. And you can see, let's see, what are we multiplying by? 1/4, it looks like. Yeah, multiplying by 1/4 each time that slope is. And so that would be the exponential function, is the base must be 1/4. Oh yeah, here it is right here. There's the equation that I used to create that. So I got 1/4 just because I noticed that the slope of the A rock, each interval, so I went to the right, was getting multiplied by 1/4. That's how I knew that. Okay, that was example 4. Let me get that out of there. So I have one more, and then I'm going to give you some questions here. Last one. This one I threw on a lot of points because I have a little bit more to show you here. All right, I want you, if you can, back at home, to try to write this one down if you haven't been already, to try to write down this one and figure this out with me, okay? I'll give you the change of x, but I want you to really focus on the change of y's here, okay? Make sure I didn't lose my spot here. Okay. I'm just going to say 9-3. Okay, hopefully you're trying this at home and you're checking my answers against your own. Now I'm going to find the A rock. The average rate of change on the first interval would be 4 divided by 1, which is 4. The second interval, it'd be 4 divided by 2, which 4 divided by 2 will equal 2. The third interval, it'll be -4 divided by 2. -2. Do we have -8 divided by 2? -4. And then we have -4 divided by 2. -2. And I've lost my spot here on the x's, which x I'm supposed to be using. I think it's 8 divided by 3. +8 divided by 3, that doesn't reduce. And then finally, 0.693 roughly divided by 2. I can go through here. I think here, if I wanted it exact, it would be 3.464. Did I do that right? 4641016. That would be the A rock there. Okay, this function has got a lot more going on. What can we determine about this function? When you look at its A rock, what are you noticing? Was the A rock always negative? Was it always positive?
Neither.
Neither. It's going back and forth. So on the interval from 0 to 1, this function is, from in here, this function is increasing. How do I know it's increasing? Because I have a positive A rock. In this area, in these intervals, my function is decreasing. And then once again, on this interval here, the function is increasing. That's because the A rocks are positive there. So here's this function is going to be increasing for a bit, then decreasing, then increasing. And I'll tell you, this pattern will continue on and on and on. Do you know what type of function sometimes increases, sometimes decreases, sometimes increases, sometimes decreases, and on and on and on? What type of function does that?
Sine.
A sinusoidal. That means it could be a sine, it could be a cosine. This will be a sinusoidal function. Very good. All right, and last thing here. What does that mean about our delta A rock? Now I first go from 4 to 2, so I first decrease by 2. Then I go from 2 to -2, so I decrease by 4. 2 to -2, and -2 to -4, I decrease by 2 again. Then from -4 to -2, I increase by 2. From 2 to 8/3, -2 to 8/3, sorry. That's like -6/3. Let's see here, -6/3. Increasing to 8/3 is I increase by 14/3. And then here, I'm increasing as well. I'm not sure how much I'm increasing by, but 8/3 is approximately 2.267. So I'm increasing by some amount, just less than 0.8. So I'm just going to say squiggly line, approximately 0.8 is what I'm increasing by there. That's not exact, but it is approximately 0.8 I'm increasing. So what can I tell you? Well, I can determine a few things here. In this area here with a negative delta A rock, in this area we are concave down. And in this area here, this function will be concave up. So what happens when you change from concave up to concave down? Insert the word we haven't seen today. We have an inflection point. Somewhere in here, we have an inflection point. The inflection point occurs when your delta A rock is exactly 0. This is as long as your A rock is not the same value, as long as there is some change in A rock, then whenever the change of A rock hits 0, we have an inflection point. So this would have an inflection point somewhere in between -2 and 2. I guess we'd have to look in here. Somewhere in between these values, we're going to have a inflection point. Okay, so let's now go look at this on a graph, so we can see this. And I would need to say, is the function increasing, decreasing? It depends on the domain on that. So here, all this, it depends. Is it concave up or concave down? Again, depends on where you are in the domain. On what intervals are the points of inflection? Well, it looks like the point of inflection to me would be between 3 and 5 if I have my table lined up correctly, which we'll see in a second. Because when you're writing these out, sometimes your numbers can start to get off. So let's go. Here we go. Desmos, let's look at this graph. Here's example 5. So here's the function I gave you. Now I'm looking at it this way. Does this appear to be a sine or a cosine function when you look at it this way? Would we call this a sine or a cosine?
Sine.
It is a sine because its y-intercept is at the midline of the function. So this is a sine. Now, as I start to show you the average rate of change, connecting each of these subsequent black dots. So whenever I connect the first two, you'll notice this is a positive secant line. So in this interval here, the function is increasing. It increases, it increases, increases. Okay, from this interval though, this looks like it's from the x value of 3 to 4. Our function starts to decrease. Now we're decreasing. Now, before I go too far, here our function was concave down because though even though the slopes were still positive, or the A rock was still positive, each A rock was less than the one that was before it. Let me see if we can see that slope here. There's the table. Let me pull this up. Oops. Let me pull that all the way up there. So you can see the slopes. As I change my A values, you'll see each slope. Let me start back over. Okay, each slope. So this slope is 4. I'm looking on this line right there. That slope is 4. This one's 2.92. You can see each slope is decreasing. Finally, we get to a negative slope. So this part was concave down. Now, if we ever had a change of our A rocks where it hits 0, that's where we'd have an inflection point. And I'm trying to think through here if I could do that. I'm trying to think of how I would type this in. I'm not so sure I know how to type that in here on the fly. But to show you, this right here would be an inflection point when we are going through this point at 6. That would be my inflection point, which I don't think 6 was on my table. So yeah, when I circled that up here earlier, this would be an inflection point right there. We would also have an inflection point at 0. Right here at 0, we'd have an inflection point. We'd have another one at 12. Mathematically, those are where they would occur. So as I continue on, right now, I'm concave up because even though my secant lines are negative on the left side, they're increasing. And now my secant line is positive, so the function starts increasing, and the slope is increasing as I go along. So in all that, we would say the function is concave up in that interval because our delta A rock went positive. That's why I was concave up. Because on this side, because my A rock itself was positive, the function is increasing. So you've heard me say a lot of different things today. A rock, delta A rock, A rock, delta A rock. Just in summary, what I want to make sure you get in summary is this, that if your A rock is greater than 0, let me put if, then your function is increasing. If the A rock is less than 0, the function decreases. And I showed you that with exponential, logarithmic, and sinusoidal function today. If the delta A rock is positive, then the function is concave up. If that delta A rock is negative, then the function is concave down. For any function that has both positive delta A rock and negative A rock, any function, all right, at a point, let's say it this way, at an interval with delta A rock equaling 0. I should say if let's say that if interval has delta rock equaling 0, then there is a point of inflection. Okay, so hopefully if you got on tonight and you saw me work through all those problems and you saw the same thing over and over, but you got that down, then tonight was a win for you. Because this is one of the things that AP your AP exam is going to be built around from Unit 1 is understanding AROC and delta AROC, the change and the average rate of change. So AROC stood for average rate of change, delta AROC, the change in the average rate of change. And visually, that would be a secant line. So the slope of the secant line would be the AROC. That's why I'm sometimes saying AROC and sometimes saying secant line, because the AROC is the slope of the secant line. So if you got that down, then tonight was a win. That was the whole goal. Okay, so Olivia here, I've got one for you. If you want your bonus, I need you to fill out this problem. Once you're done, you can snap a picture of it, send it to me through Remind. Yeah, from there, you'll earn your points. So the function of k is shown. What general statements could you make about this graph, about the AROC and the delta AROC given this graph? And finally, are there any points of inflection? Take a picture, whatever you need to do. Write down your reasoning why this is true. Make sure you give me the why. Don't just give me 2 words. Make sure you give me the reasoning why behind it. And send it in, and you will get your bonus. Whoops. I hit the wrong one.